homework. Any questions about the homework? Beza! Which one? 5, 4? Where's 5, 4 if that was 61? Oh, 64? 6. This one? Okay. Oh, I need to sit down for this. Ugh. The only thing I hate about this weather is the sticky feeling. I feel very sticky. Sticky, icky. Okay. So we got the cross sections or squares. We got all of that. And so what do we got here? Sorry about those itches. So we're used to the bottom being the XY plane and the rest of the solid being on the top, but this figure has some above and some below the plane. Let's find what's above the plane and double it. So what I'm talking about there, remember the pieces of paper that I showed last time, like we're used to just the figure sticking above the XY plane? Well, we got it above and below, but there's symmetry. So I'm just going to look above and double that. So, we got this. Now, where this picture is coming from, if we go back here, so, how do I want to describe that? Trying to figure out. So we got a cross section here, and really the thing also that's going on, like with these circles, these circles have the equation x squared plus y squared equals r squared. And if we solve for y, we get this thing. And so that's where I'm getting this from. So the side is on the y-axis. So like top minus bottom is the circle minus the x-axis, which is 0. Hang on, I gotta blow my nose. So that's where I'm getting the equation for the side of the square. Or the side of that 1/4 of the square there. So any questions about this part? Yes, Surat.
I don't understand how the square is a circle. And you need the equation of the circle for that is the square.
Well, where's my pointer? Oh, I'm already on the pointer. This part falls wherever the radius is. So it's not that the circle is a square or anything. It's just that this distance is the radius of the circle, but we're just making a square from that radius. Sorry, it's hot. Let me see, can I... I'm trying to think. It's kind of like this. Let's actually look head on at a cylinder. So we have it when the, like, depending on where the square is. So the square could be at the top, and then this is where I can't draw it, because this is actually like in here, in there. Oh, this is so bad. Hang on one second. I'm going to put a layer. Wait, I want to erase the picture. So, you know, we have the square kind of in here. So it could be here. As the square goes down, the cross section, that top will go down further like that. So here's the words are hard. Here is the center of the circle. And I'm going to draw this differently. So here's the center of the circle, and you have this going across here. So here's R. This is your y coordinate, and this is your x coordinate. So that's what I'm talking about. This is going up R units. Actually, I guess I should say y. It's really the cross. But but that's where I'm getting the x squared plus y squared equals r squared from, is from this triangle in there. If that makes any sense. And then, I mean, this is really the battle right there, is getting that. Does that make sense? Sorry, I can't draw it. I'm sorry, your math teacher's not an artist. Ooh, we're going to have to do a lot of artwork today. So once we get that, then remember the formula is the integral of the area of a cross section. And we're multiplying by 4 because I'm only looking at 1/4 of the square, but then we're also doubling it because we're looking at top and bottom. And so, I mean, like I said, this is the battle right there. But then once you get that, it falls into place. This is another one of those big challenge problems. This is like a separator of an A- from an A+ student. In case, like, that's what I would consider this kind of question. So, any questions about that though, or anything else? I can hear a pin drop. Arr! Oh, was that a hand up, OJ?
Is that a coincidence that it's like 4 times the volume of a spin?
I don't know. That's a good question. Maybe. Maybe not. There might be a way to think about rearranging it. You know how, like, you can take a parallelogram and cut off part and put it over here, make a rectangle. I don't know. There might be a way to, like, piece it apart and make a sphere, make 4 spheres out of it. That's a good question. Can I have your homework then? And there's no reality check today, eh?
Oh, that's a little
Thank you very much. All right. Well, we are going to do another type of volume today. Volume by the disk method. So, I have some prepared pictures here, but then I will, on the next page, try to draw. So, don't worry about trying to draw these initial pictures. I have a little video we're going to watch. Oh, actually, you know what? While we're doing that, I have to make sure I'm on the internet. You guys can write down the section title while I make sure I'm on the internet. Not that that's really a secret, but I can only with my tablet get on the guest network, so it won't be very exciting. Maybe. Oh. I guess if I can always do it on my computer. No, I can't even get this on there. Oh, wait. Oh, nope. Wait. Ah, there we go. Okay. So hopefully you guys have the title down by now. So here's what's going to happen. I'm going to do my best to describe it, but then we're going to watch a quick little video that's going to show it, and then we're going to do our best to draw our own pictures so you can see it. But what we're going to do, again, remember like taking the area and cutting it up into rectangles. Imagine that this rectangle is one of those rectangles from the area. If this line is our axis of revolution, imagine I could spin it, this rectangle there. As it spins around, it's going to make this disk. So now what we're going to do, instead of dividing the area up into cross sections, because these are areas, we call them volumes of revolution, because we're going to take some area, we're going to rotate it about an axis of rotation, and it's going to create this rounded area of some sort. So we're going to take the area and cut it up into these disks, or the volume and cut it up into these disks. So here's now this idea on a bigger figure. So imagine this blue area. This is one of those representative rectangles. As the area rotates around the axis, it would make this blue shape. Kind of cool. Anybody ever do any woodworking on a lathe? It's kind of like that. If you're ever looking for those videos, you know, to put you to sleep, woodworking on a lathe videos. Those are actually every time. Anyway, so this is a representative disk, and this would be an example of like all the disks that would make up that figure if we're, you know, if we're going to use 6 different sub-intervals. So do you see what's happening in the picture? Now this is when the area actually touches the axis of rotation. It makes a disk. If this rectangle was like a little bit above the axis of rotation, it would create a hole in it and would actually create a washer. So let's take a look at this. Let's see if this works. So it's just a very quick, like 40-second video. But you can see here's the area, and we're going to rotate about the x-axis. So there it is rotating. And you can see that hole in the middle. And then there is a disc with a hole in it. We call it a washer because it looks just like a washer you would have. So we're going to look at volume by discs where there is no hole, but also volume by washers where there is a hole. And they're actually very similar. That's the end of the exciting video. But does that make sense? Does that help you see what's going on here? Okay. All right. So let's go back to the notes. And let's try to draw for ourselves. So let's first look at a disk. Now the disk, the rectangle could spin vertically, but the rectangle could also spin horizontally. So we're going to have disks that are vertical, we're going to have disks that are horizontal. I'm going to draw a horizontal one here. So it is a disk, it is a round figure made up of circles, so I do have a radius. I'll just call it with a capital R. And this disk does have a thickness to it. It has a height. In this case, since I've drawn the disk horizontally like this will be like a delta Y. When we draw it vertically, it's going to have a thickness along the x-axis. It'll be a delta X. But the volume of this disk would be pi r squared h. And that h could be delta Y or delta X. Now for a washer, not a whole lot different. So I'm first going to draw a disk. I'll make it a little bigger because I want to draw stuff inside it. So we start with a disk, but then we cut a hole out of it. And there's our washer. So I still have a big radius. It didn't show up so well, but the pink is a capital R, which we'll call the outer radius. But then we have the radius of the hole. So we can see that the volume of this washer is going to be the volume of the big disc, and we're going to take away the volume of the hole. So I'm going to call the inner radius with a little r, and this is the inner radius. And then similarly, we have this height of the washer, which could be delta x or delta y. So volume of a washer is basically like doing the volume of a disc twice, because you're going to have the volume of the big disc, but then you got to take away the volume of the hole. And then the only thing I'm going to do with this formula, I can factor out a pi and an h. I'm going to factor it out kind of weird, but it'll make sense when we put it into an integral. I'm going to factor out the pi in the front, and I'm going to put the h at the end. So, any questions on these? And then this is just one disc or one washer, but as we saw from this picture, we're going to have multiple discs or multiple washers. So we have the sum of all of them to approximate the volume of the big figure. But then through the limit process and putting in an infinite number of discs or washers, we get the actual volume, and that's what creates our definite integral. So I'm going to skip writing all that stuff. But for a disc, it will just become, we usually factor out the pi and put it in front of the integral. But it's just pi r squared h, which in this case is a dy. It can be a dx also. And then similarly for the washer, the volume is pi times the integral of the outer radius squared minus the inner radius squared. And again, it can be a dx or a dy problem. The way I've drawn it horizontally like this, it's a dy. So we have this. So it's going to be just like last night's homework. It was all about finding the formula for the area of a cross section. Now it's going to be about finding formulas for these radii. And the good news is, I actually think these are easier. So any questions about that? Yes, Mason.
What are the C and the D?
They're just your limits. So I'm about to draw a picture like with the actual thing, but when we look at the shaded region that's being rotated, in this case, since it's dy, you look at where that shaded region goes from on the y-axis. So what's the lowest point, what's the highest point? But it's whatever the limits are. So, any other questions? That's a good one. All right, so let's do that then. Let's try to put this in context of a bigger picture. So, we're going to do volumes of revolution. Let's try to draw one first with a disc, and then we'll try to draw one with a washer. Volumes of revolution. And this will be discs. So we're going to do something similar to what that picture is above that I showed. So, imagine, if you will, let's take this region here, bounded by the curve and the x-axis. And this is going to go from A to B. And we're going to take this area. And in this case, we're going to rotate about the x-axis. So as it rotates, it's going to make kind of this vase shape on its side. So we'll have this kind of thing happening there. Maybe it's a bell. If you look at it the other way, it's a bell. You know those party decorations? They're made out of crepe paper, and you open them up and you kind of like, they unfold and they make Christmas ornaments, or they often make bells or whatever, circles. It's like a volume of Revolution. Anyway, so imagine if I had taken this area and cut it up into the rectangles like we've done before. But let's just take one of those rectangles. This will be our representative rectangle. That's why we call it the representative rectangle. It's representing one of the rectangles in the picture. So as that rectangle spins around the x-axis, that is what's going to create the disk. This thicker. Maybe it'll show it better thicker. Woo. So there's our disk. And then we can see that the radius is measured from the axis of rotation to the end of the rectangle. So the length of the rectangle is going to give you the radius. In this case, it would be a top minus bottom problem because it's going vertically. If it was horizontally, it would be right minus left. So the volume is pi times the integral, big R squared, and in this case it's a dx problem. And now we can see those limits of integration where they're coming from. So any questions about that? Let's try to do a disc now. I mean a washer. Wood. So washers. Yeah, I got room. Anybody still need the disc or have any questions on the disc? Yes, Kenny. Oh, you still need it? Okay. Anybody have any questions? All right. All right, anybody still need it? Okay, let's do a washer. So we'll set up our axes. And this time we'll take this region. It's a pretty flower. It's a petal. I don't know why, over break, I started, like it showed up on my YouTube feed, and so I just got sucked in and started watching the beehive videos. Have you ever watched those, beekeeping, where they capture swarms of bees? I don't know how they do it. They'll like stick their hand in a swarm of bees. I know, right? And I'm a big baby when it comes to bees. I admit it. Big old baby when it comes to bees or spiders. It's insects, bugs. Oh, ugh. Mosquitoes freak me out. You know when they do those flybys your ears? Buzz. How many of you guys are like right now just going, oh, stop. Okay, anyway, let's talk about something better like washers. Okay, so I'm going to take the same region, rotate it about the x-axis. So we know that it would end up tracing something like that. Be kind of a weird thing. On the outside it would look like a bowl, but on the inside it would look like a funnel. Kind of cool. And again, let's imagine if we did have this cut into rectangles. And I'll take one of those rectangles as my representative rectangle. I'm going to pick on this guy right here. And as it rotates around, it would, use a different color actually, it would make this is not a great picture, but it would make something like this. Let's make that thicker maybe. The other one wasn't bad, this one sucks. But we can see that hole in there, that disc, or washer. Hopefully you guys can see the washer that I'm trying to draw. That is horrible. So this time, and I'm going to draw a more simple picture where we'll be able to clearly label it on there. But this time we have an outer and an inner radius. The outer, I'm not even going to try to label it because it's going to make this picture worse. But the outer radius, you can see, is measured from the axis of rotation to the furthest point of the rectangle. That would be the outer radius. And then the inner radius goes from the axis of rotation to the closest point in the rectangle. And that would make up the inner radius. So keep that in mind when we draw the simpler pictures. I'll label it there. But again, we have this. I tried to practice my pictures yesterday, actually. I put this, my little cheat sheet, as me practicing my pictures because I'm so bad at drawing pictures. But any questions on what's going on here? Because now we're going to put it down a little more formally. All right. Anybody still need this? In our simpler pictures, I'm just going to draw the representative rectangle. But I wanted to get this down so we could see what I mean by the representative rectangle. Anybody still need these? Alrighty, so volumes of revolution. There's actually 3 methods for finding volumes of revolution. We're doing 2 of them today, discs and washers, because they're so similar to each other. There's another method we'll do on Tuesday next week called shells. So, this one is discs and washers. So let's first do discs. Now your axis of rotation could be vertical or horizontal. And just like the cross sections, that's what's going to dictate if it's a vertical or a dx or a dy problem. So if you have a vertical axis of rotation, it will look like this. You'll have the vertical axis of rotation, which could be the y-axis, but it could be a different vertical line, and we'll see how to do that. It's actually not that big a deal, but it doesn't have to be the y-axis. And then the representative rectangle is always perpendicular to your axis of rotation. Let me spin around this. So as long as that representative rectangle is touching the axis of rotation, it's a disk. It won't make a hole. So we can see that the radius is just simply the length of that representative rectangle. And so the volume, actually I'll just say V, is pi times the integral from a to b of big R squared. Is this a dx or a dy problem? What do you think? Look at the thickness of the rectangle. Is that along the y or the x-axis? Be along the y. So this thickness here, wherever the y-axis is, I would eventually go to the y-axis. It would be along the y-axis. That's what I mean by along the y-axis. So a vertical axis of rotation is going to make a dx problem, but if you have a horizontal axis of rotation, again, always draw your representative rectangle perpendicular to the axis of rotation. For disks and washers, it's always perpendicular. And now we can see it's a delta x problem. I'll put delta y here. So this time the volume is pi times the integral from c to d, just whatever, dx. So there's disks. Now we're going to draw something similar for washers. Any questions about what I'm saying here? These are some of my favorite problems we do all year. They're fun. Oh, no. Anybody still need this? Okay. Anybody got plans over the weekend? What are you doing, Charlie? Oh, really? Is it going to rain? I don't know what the weather is. Do you like doing track in the rain? Okay, well then I hope it rains. Yay! When is the track meet?
Oh, yeah. And right with Michael, 17 miles on Sunday. Very Friday.
Did he turn 17? Oh my god. You guys are weirdos. Did you do so, you're talking Michael Ferroni?
Yeah.
So have you guys done a marathon then?
No.
Have you done a half marathon? I mean, you basically did. Just you should do it for fun. Just do one of the races. It's fun when you're like with a whole bunch of people, and that's awesome. Wow, I'm impressed. You guys are nuts, but I'm impressed. You have a strange sense of fun. Anybody else do anything exciting? I'm going to grade your tests. Yeah, I know, right? I've actually started. I mean, it's not like I haven't done anything. All right, let's do washers. So again, we're going to do vertical and horizontal axes of rotation. So if it's a vertical axis of rotation, I'll draw a vertical line that is not necessarily the y-axis, but could be. Now, if it's going to make a washer, this time the representative rectangle will not touch the axis of rotation. It's going to make a hole as it rotates around. So I'm going to label the big R and the little r a little differently than I did up above. As it rotates around, your big R is going to go from the axis of rotation to the outer part of the rectangle. And then your inner radius is from the axis of the center, the axis of rotation, to the closest part of the rectangle. That's what's going to make the hole. So try to visualize that when you're doing these, is where the big R and the little r goes. Because it does differentiate between the washers and the discs. So then this volume is pi big R squared minus little r squared. And the way I've drawn it here is a dy problem. And then we'll do something similar for the horizontal axis of rotation. Horizontal axis of rotation. You got to admit, whoever came up with this, whoever visualized this in the first place, pretty brilliant. The inner radius is from the axis of rotation to the closest part of the rectangle. The outer radius will be from the axis of rotation to the furthest part of the rectangle. And this will make a dx problem. So the volume is pi times the integral from c to d, big R squared minus little r squared. Dx. Dun, 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 dun. Boop, 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 boop. Enough of this. Let's do an actual example, huh? I got 2 examples, kind of 3, because of course one of my examples has to have 2 parts. Kind of like your homework had 4 problems on it. Or was it 7? Sorry. How many, oh, you know what? That's what I'm going to do. Next time a student asks me how many questions are on the test, 1. There's 20 parts, but there's 1. All right. Anybody still need this? Now you know my secret. I gave it away. I shouldn't have. There we go. Write this down. Region bounded by the parabola y equals 4 minus x squared in quadrant 1 is rotated about the x-axis. Find the volume. And try drawing the picture. I will freeze. Freeze. It's one person. Did you guys draw the picture yet? Charlie, you're inspiring me to get on my treadmill this weekend. I need to start doing something again. Thank you. Here's the picture. It's a parabola that opens up, down. If you find the intercepts, it's pretty easy to draw. Again, notice I'm not really worrying about drawing it to scale. Godzilla! Just made a parabola. So any questions there? All right. I do want to see that representative rectangle on your pictures. So which way should I draw mine? Should I draw it vertically or horizontally? Yeah, I see some hands going like this. Always, for discs and washers, it's always drawn perpendicular to the axis of rotation. So if we're rotating about the x-axis, it's got to be a vertical rectangle that goes around. So I shall draw a representative rectangle, just a random rectangle somewhere in this region. So does that make it a dx or a dy problem? It's a dx problem. And by the way, I think I might have said it and given it away, but is this a disc or a washer?
Yes.
Right. Now, I do want to point out something. So everywhere in this region, as that rectangle is drawn across it, the rectangle will always touch the axis of rotation. If there's just any point where it doesn't, make it a washer problem. But the good news is you don't it might touch sometimes, but not others. The good news is you don't have to make two different integrals because of that. Just treat it like a washer problem and that will take care of it. But this never creates a hole, so it's a disk all the way through. We're going to treat it like a disk problem. And like you guys said, it's a dx problem. So we only have to find one radius. And this radius, is it a top minus bottom or right minus left? Yep, top minus bottom because it's vertical. So we just have to figure out what the equation is on the top and what the equation is on the bottom and make our radius from that. So, as this representative rectangle is drawn across the region, is it always the same graph on the top? Oh, thank goodness, yeah, it's always the parabola, isn't it? So the parabola is always on the top, and is it always the same curve on the bottom? Yeah. It's just the x-axis on the bottom, which is y equals 0. And our equation's already in terms of x, so that's also fortunate. So on the top, it's y equals 4 minus x squared. And on the bottom, it's y equals 0. So our top is 4 minus x squared. Our bottom is 0. So the radius is just 4 minus x squared. It all falls into place after this, so I want to make sure we're cool here at this point. Any questions there? So we just plug into our formula and see what kind of integral we got. So the volume is, it would be pi times the integral of r squared dx, but r is 4 minus x squared. Just don't forget the squared, the other squared on the outside. What are my limits of integration going to be? 0 to 2. It's a dx problem, so look along the x-axis where the shaded region is. And we won't actually take the time to solve it, but I'm just curious, if we were going to, can anybody tell us what we would have to do to solve this? Yeah. We'd have to first expand it, if you were going to do this by hand. Uh-huh. Excellent. And then that would be easy to integrate and plug in and stuff. I'm just going to go ahead and actually here, let me so with these, we've got a pi in them. The answer is going to be in terms of pi. So when you do the, like if you're going to use the calculator, don't put the pi in the calculator. Wait. Where's my calculator? There's my calculator. So here's what I mean. If I put the pi in there, pi, and then math 9 from 0 to 2, and I'm going to have to put another set of parentheses here because I need to, there we go. I need to take that expression and square it. But if I go ahead and enter it in with the pi, I get this, but then I try to change it to a fraction. Oh, actually, boy, that's very weird because pi is irrational. It actually shouldn't have been able to change this to a fraction. So this is just an approximation. It's actually, I'm sure it's a very good approximation, but it's just an approximation. You won't see that on a multiple choice test, though. Instead, here's what you do. Just enter this in without the pi. Change that to a fraction, 256 over 15, and then your answer, whoops, is 256 pi over 15. That's what you would see on a multiple choice test. And most of the time, when you put the problem in with a pi, if you try to change to a fraction, it actually won't be able to. That's just very weird that it came up with something. So any questions about that? So the whole thing, the whole game is going to be finding the radii. That's all it is. So let's do one more problem. See, look at that. That didn't take us very long at all. Anybody still need this before I go to the next problem? I keep saying we have one more. Let me make sure I didn't lie to you. Oh, but I did lie to you. I forgot it's got 4 parts. I didn't do that. I didn't lie to you on purpose. I actually forgot. Look, we're going to rotate this. Whatever this region is, we're going to rotate it about the x-axis and then the y-axis and then the line y equals 8 and then the line x equals 2. Oh my God, this is going to be so much fun. Let's do it. All right. First, let's just draw the region. And then we'll have to repeat it for all 4 parts. So see if you can figure out what the region looks like. Take a moment. I'm going to freeze my screen again. And then we'll see if we get the same region. damn phones. You know what scares me as a teacher? And it's coming soon, sooner than I want. AR glasses. And have you seen any of the renderings? I mean, it's all rumor at this point, of course, but have you guys seen any of the renderings of what people think Apple might come up with? Oh, yeah. Does anybody still need this one? While I'm telling you about my fear as a teacher. You got a brief glance at the other problem there. But the renderings actually look like fairly normal glasses. Like very similar to what you're wearing, Derek. Just regular old glasses. Nothing to indicate that there's a screen that Derek can see and look up all the answers on a test. Yeah, but you know people will find ways of replacing the arms or whatever and putting something different. It won't be, I mean, the first glasses will probably be obvious still, but it won't be long. I need to retire soon. But the bad part is, because I love gadgets, I want one of those. I want a pair of those glasses so badly. But they also scare me in the classroom. All right. Oh, sorry. Was that enough, David? Okay. So here's what the picture is. And we're just going to draw this picture over and over and over again. It's a simple picture to repeat, though. But any questions on the picture? So, by the way, like, sometimes it's not so obvious. But I'm just going to go ahead and just quickly put, because if you put the whole parabola, and then you put the line, and then you have this, like it may not be so, let me actually redraw this real quick. So you put the parabola, you put the line, you put this, like, what is the region that's, sometimes it helps if you either use different colors, or like if I make it, let's actually make this really bold. Bold! And then we have this, and now it's making it so small. But there's just this little tiny part that's actually got bordered by all three curves. So you have to imagine what part actually is bordered. If you were thinking maybe it was this part up, oh, I was meant to change colors. Maybe it was this part up here. Well, the problem is that there's no border on the top. There's nothing bordering here, nothing. Anyway, so it's got to be bounded by each region, or each curve. So any questions on the region? Okay, let's do it. Let's first rotate about the x-axis. So, part A, about the x-axis. We'll do the x-axis together, and then I'm going to have you guys set up the y-axis. So I'm going to redraw the picture. We're going to redraw it every single time, but like I said, this is an easy picture to draw every single time. Not a big deal. Which way do I draw my rectangle if it's rotating about the x-axis? Horizontally or vertically? Yep, vertically again. What do you think? Is this going to make a disc or a washer? It's going to make a disc. That rectangle, as it moves across the region, is always going to touch the axis of rotation. It's a disc, baby! Is it a dx or a dy problem? All right. So we only have to find the one radius. Is it top minus bottom or right minus left? Top minus bottom. It's drawn vertically. Is it the same curve on the top all the way through? Yep. Oh, thank God. What is that curve? Yes. What is on the bottom? Yes. So the radius is just 2x squared. Any questions about that? Alrighty. Can anybody tell me what the integral is then that we're going to use to solve this? The volume will then be what? Yo, Jay!
Pi integral 0 to 2x squared in parentheses to the second power dx.
Perfect. That is it. This would be super easy to do by hand. I'm just going to go ahead and do this though. So when you use the calculator, you will get 128 pi over 5. Ta-da! Now again, I'm going to say like what I've said before. I encourage you to practice using the calculator, but I also encourage you, if you need help with still like integrating, also practice doing it by hand. Try both. If you feel really confident about the integrating by hand and you just want to use a calculator, I'm okay with that. Remember, it's going to show up on the test, which is 70% of your grade. So I trust you guys to make the wise choice. You do what you need to do. But any questions about that? Because now I want you on your own to try part B about the y-axis. I'm going to pause the video too. Pause. So your rectangle will not always be touching your axis of rotation. That's what's going to make the hole in there, and that's what's going to make it a washer. And then I kind of gave it away already too. This is a dy problem because the thickness of that rectangle is along the y-axis. And then remember where you're measuring the radius, the big R and the little r from. The big R goes from the axis of rotation to the outside of the rectangle. So that distance is big R. And then the little r will go from the axis of rotation, ooh, that's a crummy little bracket, to the closest part of the axis of rotation. Are they both right minus left or top minus bottom? Right minus left. So take a moment to think about what the big R and little r is going to look like, and then we'll check in on that. All right, so here's the big R and little r for this one. The big R is actually a constant radius. Makes sense because it's along a vertical line, but you can also think of the right equation as x equals 2. The left equation is x equals 0. So 2 minus 0 is 2. But for the little r, it's going to be along the parabola. And remember, since this is a dy problem, you're going to have to take that equation for the parabola and solve for x. Put it in terms of y to get your right function. So any questions about that? This is, once you got this, then you're on the home stretch, because you just plug into the equation. So we'll finish it up together. Try writing. I won't pause it. I won't say it though. Try writing it on your own, and then we can check together. What are my limits of integration going to be? Super?
Is it 0 to 8?
Yes. Remember, since it's a dy problem now, our limits have to go along the y-axis. And I could clean this up a little to make it easier to put on my calculator. And also if I was going to do this by hand. Turns out it's not that bad to integrate. And actually, the answer is just 16 pi. So any questions on this one? Yeah, I just plugged it in. I cheated. I used a Calco cheater. I admit it. Any questions? All right, let's try C. What was C? About the line y equals 8. Does anybody still need this? Say it again, because the second term. What are we looking here? Okay. Yeah, I mean, I could have used a y. I could have done the alpha y on the calculator, but I just used an x because you got that nice button. Alrighty. Any other questions? Now I already forgot what C was. Y equals 8. Alright, C. About y equals 8. So we'll do this one together, and then I'll have you guys do part D on your own. So C, I'm going to draw that same picture. That's at 2, 8. We got this area that's going to rotate about the line y equals 8, which is up here. That's crazy. Which way shall I draw my representative rectangle? Horizontally? Oops. Horizontally or vertically? Vertically. Always perpendicular to the axis of rotation. So I'm going to draw that rectangle right here. Will that make it a disc or a washer problem? I think I heard both. I heard one voice say disc and one voice say washer. Trey, can you convince us why washer? You trailed off at the end. Instead of it looking at it touching y equals 0.
Instead of making sure the rectangle always touches y equals 0, you have to make sure to look at y equals 8.
Why do we have to look at y equals 8? Exactly. Look at the axis. Ooh. Look at the axis of rotation. Does this rectangle always touch the axis of rotation? It will touch right at the very end. But there is at least one place where it does not touch the axis of rotation. That will make a hole. That's a washer. Is it a dx or a dy problem? Dx. So any questions on the washer or dx part? So then we have the big R and the little r we got to worry about. So the big R, remember, goes from the axis of rotation to the furthest part of the rectangle. Is that a top minus bottom or right minus left? Yep, top minus bottom. It's vertical. We're going to measure up and down. So what equation is along the top? Y equals 8. And what is along the bottom? Y equals 0. My big radius is 8. And it does make sense that we get a constant because we can see actually that both the top and the bottom are parallel. It's going to measure the same distance all the way across. The little r. So little r, remember, measures from the axis of rotation to the closest part of the rectangle. What is along the top there? This distance will always follow the line y equals 8. What about the bottom of the little r? As this rectangle moves across the region, what's the equation that this traces? Y equals 2x squared. And that actually doesn't simplify, so there's my little r right there. 8 minus 2x squared. And then we literally just plug into the formula. The volume is pi times the integral big R squared minus little r squared. And we already said it was a dx problem. What are the limits of integration going to be? Sufrit? It is. We're along the x-axis this time because it's a dx problem. And make sure I got all the squareds where I need them. This one works out to be 896 pi over 15. So I'll put D down here. You guys can look at this still if you need it, or D is at the very bottom in case you didn't write it down, or it's, you know, whatever. Anyway, it's about the line x equals 2. So you guys try that one on your own, and we'll check in. I'll pause the video. Washer problem. It is a disk. You should have found that the rectangle will always touch the axis of rotation as it's moving down. So we only need one radius, which is the length of the rectangle. I should have put right minus left to remind us, just for our notes. Whoop. Right minus left. Any questions about this? Yes.
Oh, when I typed it into my calculator, I did not get like a fraction, and I did exactly what.
That's a good question. Same thing happened to me. Let me show this. So first of all, if we take a look at this problem, well, anyway, I mean, we do have a square root in there, so we may get some weird stuff, but look what happens when we go to the calculator on this particular one. So, hold on. I already forgot the thing. Let me look at my calculator to remind me. So, math 9, we're going from 0 to 8 because it was a dy problem. Right was 2. Oh, actually, hang on one second. I'm going to need Hang on, let me try this again. Okay, I need one set of parentheses there, then 2 minus the square root. And I'm just going to use x's because it's easier. Close my parenthesis and square it. dx. There we go. So that's the integral. So I get this. And this is the same thing I got on my handheld one. And I try that math, change to fraction. How the heck did I get my 16 over whatever? I don't remember what the fraction was. Well, I'm very suspicious. I know something about the integral, and like it's, I mean, yeah, I've got the square root, but there's no like funky thing like sine or cosine or anything that's going to give me really weird stuff. And I'm looking at that. A whole bunch of 3's started repeating until the end. I'm really suspicious. Again, your calculator is just, it also is doing approximation methods to do these problems. When you guys take Calc BC, when we get to the infinite series chapter, the unit in there, we'll actually look at some of the approximation methods that these calculators could be using. I'm not exactly sure what approximation methods these calculators use, but they are just calculating this stuff. This integral is just being calculated using a numerical method. meaning it's not actually finding the antiderivative and then plugging in the upper and the lower limit like we would do by hand. So what I did, and Arena, yeah? It is a dy problem, but this is what I was talking about before. Like, if I look at this integral, just to use the calculator, as long as I make these variables all match, it's fine. So because I have a button on the calculator to get x super easy, I just make them x's when I use the calculator. So everything was an x. So all I did, I know that 0.3 repeating is 1/3. So I got my I could have done, this one's easy enough, 5 1/3. That's 16/3. If it's one of those ugly numbers though that you can't just do in your head like that, you can do 5 plus 1/3. Get that on the calculator and then change to fraction, and it will do that one. But yeah, this one actually couldn't change it to a fraction for me. We had to know a little bit. That's why we can't just rely on the calculator to do everything. We still have to know a little bit. It might, but it's also using the power, like a much more powerful processor than these calculators are. So, any questions about that? Either the process of doing this or the calculator stuff. All right, that's it then. That is the end of the notes. Let me get you your homework packet.